In this video, I'll explore using multiple tables on an OpenFlow enabled switch. In particular, I'll do this with OpenVSwitch via Mininet network emulation. Using multiple tables, I'll configure a single OVS switch to have access control rules like traditional router ACLs, to do network address translation, and to route between two different subnets. This video is a follow-up to my introductory videos on OpenFlow, OpenVSwitch, and flow entries with OpenFlow switches. OpenFlow tables. When a packet arrives at an OpenFlow switch, the processing pipeline begins with the lowest numbered table. Tables contain flow entries that have match fields, actions to take, and track statistics. The highest priority flow entry in a table that matches a packet is the one that will be used. The action might be to leave the processing pipeline. Example actions are sending out one or more ports, drop, flood, or send the packet to an OpenFlow controller in a packet in message. The action instead might be to send the packet to a different table numbered higher than the current one. For example, a packet might be processed by table 0, then table 1, then table 10, but you have to move forward through the table numbers. A good use of this processing pipeline would be to separate out logical functions. This is analogous to order of operations on traditional router interfaces. For example, a router may first check input firewall rules, then QoS parameters, followed by any NAT rules, and so on, going like that through different logical features before being sent out a destination interface. This diagram shows the topology for this video using Mininet network emulation. The OpenFlow switch is S1 and is OpenVSwitch. H1 and H2 have IPs 10.0.0.1 and 10.0.0.2, so they are in the same subnet. H3 is in a separate subnet with IP 30.0.0.3. On H3, I'll start a port 80 web server. I'll launch Mininet with the Mac option so we get these simple Macs shown here. Also note the OpenFlow ports 1, 2, and 3, which will be used for our forwarding actions. This diagram shows how I'll set up flow tables on switch S1. When a packet arrives, first table 0 is checked, which I'm calling the access control table. In this table, I'll define rules similar to router access control lists. In the first flow entry, I'll permit ARP and IP between any 10.0.0.0/24 IPs. In the next flow entry, I'll permit H1 to reach H3 via ICMP or TCP port 80. Next, I'll allow any traffic from H3. For those three permits, the action will be the same, which is to continue on through the processing pipeline onto table 1. Finally, in table 0, there is the default drop, meaning any traffic that doesn't match the previous conditions will be dropped and of course not make it to table 1 for processing. For example, H2, which is at 10.0.0.2, will not be permitted to reach H3 because there is no explicit rule to allow that. Table 1 has NAT rules. When H1 connects to H3, I'll say that H1's source IP should be changed to 5.5.5.5 and to continue through the pipeline to table 2. For the return traffic, I'll say traffic to 5.5.5 from H3 should be natted back to 10.0.0.1, also with an action to go to table 2. Then there will be a default rule for any other packets not matching these first two rules just to go to table 2. So unlike the access control table, by default we can continue on in the processing pipeline. In this last table, I'm setting simple rules so hosts can reach one another, even on different subnets. This will be done by matching on the destination IP address and using that to set the proper destination MAC address. What I'll do to my hosts so this can work is I'll give them a dummy default gateway and a dummy ARP entry to reach the default gateway. This will keep my host from sending out ARP requests for a default gateway. As long as a packet gets to my OpenFlow switch, I can manipulate it correctly to get to another host on a different subnet. This isn't dynamic or using a routing protocol as a traditional router would, but that functionality could be reproduced in an OpenFlow controller. Also in this table, I'll put rules for ARP between H1 and H2. Here I am on a Mininet VM. I'll launch the topology shown in the Visio diagram previously. Now for some adjustments to the three hosts H1 through H3. For H1, I'm giving a default gateway that doesn't even exist. It will be 10.0.0.254. And then I assign a static ARP entry so it thinks it knows how to reach 10.0.0.254 and doesn't need to do an ARP request for a gateway. For H2, I'll do the same thing. And now some commands for H3. For H3, I'm assigning it IP address 30.0.0.3 because Mininet launches it with 10.0.0.3, so I'm changing that. I could have used a custom Mininet topology, but it was easy to just use ifconfig here. Then I do the same default gateway and ARP trick. Also on H3, I launch a Python web server on port 80. Adding flow entries. Now all I have to do is load up my flow entries. In a previous video on flow entries, I pasted in flow entries one by one. Here I'll do them all in one swoop using a text file. Here's what the file looks like. Table 0 is for access control like a traditional router ACL. The first two flow entries are permits between any 10.0.0/24 IPs for IP and ARP. Next, ICMP and TCP port 80 are allowed from H1 to H3. All these entries have an action to continue on in the processing pipeline to table 1. This is done with the resubmit action. This action allows you to specify a table as well as an ingress port for the next table. Here I'm only specifying the next table to use. That's why there is a comma before the 1. Finally, there is a priority 0 drop action for any packets that are not explicitly permitted. I put this here to make it like an ACL, which has an explicit deny all at the end. Table 1 has the NAT rules. So any packets from 10.0.0.1 to 30.0.0.3 H1 to H3, for those the source IP is changed to 5.5.5.5. That is done with the mod_nw_src action. Then there is a flow entry for the return traffic, turning packets with a destination of 5.5.5.5 back to the real IP of 10.0.0.1. That's with the mod_nw_dst action. These flow entries both also have an action to continue through the processing pipeline to table 2. Finally, the default rule here is just to continue on to table 2, not a default drop like the access control table 0, which makes sense. Finally are my flow entries for table 2. This one just sends packets out the correct port with the correct destination MAC address to replace the need for a gateway or a real router. The mod_DL_DST action changes destination MAC addresses. Also, there are two rules to send ARP requests for H1 and H2 out the correct ports. Since I have all these rules in a file named tables.txt, I can easily add them to OpenFlow switch S1 with one command. Let's make sure all my rules worked. H1 and H2 should be able to ping each other. So H1 will ping H2 at a count of 2. You'll see that works fine. H1 should also be able to ping H3 in a different subnet at 30.0.0.3. So we'll do H1 ping, do count of 2, 30.0.0.3. And we can see that works. H2 we didn't allow to talk to H3, so let's confirm that H2 cannot also reach H3. So here our access control table prevented this action. To verify the NAT rules worked correctly, let's quickly look at a Wireshark capture from H1. Here we see H1 at 10.0.0.1 pinging H3 at 30.0.0.3, and this is as expected. This is pre-NAT. Here, however, we see a capture from H3's point of view. It's seeing a source IP address of 5.5.5.5. And its return traffic, it's sending to 5.5.5.5. So this is post-NAT. Finally, let's briefly confirm we can reach our web server from H1 to H3. So we'll just do H1 curl to H3's IP address. And we see that works, and we got an HTTP response just fine. That wraps up this video on multiple tables on OpenFlow enabled switches. If you want to see more content like this, please subscribe to my YouTube channel. If you'd like to connect, you can reach me through LinkedIn at www.linkedin.com/in/David Mahler.